Hi, I'm Carl, and in this video we're going to have a look at questions 1 to 5 of section 3 of the orange booklet. So this is a question about the Fick method of measuring the rate of flow through a closed system. We've got a diagram which is figure 1, which I haven't copied out here, which has a look at the circulation of a fetus. It talks about two structures, the ductus arteriosus and the foramen ovale, and how they close after birth and how that can change the flow of blood through the system. Question 1 says, at which of the following points will the blood passing the point be more oxygenated after birth than before it? So I think the best thing to do, first of all, is have a look at these two structures. And if these two pathways through which the blood can flow is closed, how would that affect the movement of the blood around the system? So let's go through the different answers. If we look at point M, which is for answer A, this is going to be on the left-hand side, and it's going to be the vena cava entering the right-hand side of the heart. Before birth, we're getting blood flow into there from the fetal vein, which will be carrying oxygenated blood from the mother. So it's going to be oxygenated before birth. But after birth, of course, it's going to be the vena cava, and it's going to be returning blood from the systemic circulation. So it's going to be more deoxygenated after birth than before it. So it's not going to be A. If we look at B, then that talks about point N, which is in the left ventricle. So at this point, before birth, we're getting some partially deoxygenated blood. So we've got oxygenated blood going through the pulmonary circulation of the fetus. Now, obviously, there's not going to be any gaseous exchange in the lungs at this point. So after blood is passed through these tissues, some of the oxygen will be removed, meaning that before birth, it's going to be partially deoxygenated at point N. But after birth, it's going to be getting blood straight from the lungs after oxygen has been absorbed. And that means it's going to be more oxygenated after birth at this point than before it. So the answer for number 1 is going to be N, or B. If we look at number 2 then, it says at which the following points will blood passing the point be significantly less oxygenated after birth than before it. Note that they've said significantly less oxygenated. Again, I think it's worth just going through the different options here. So if we look at A, we're going to have a look at option K then. So that's going to be the aorta here. This is blood leaving the left ventricle. We said that before birth, leaving the left ventricle, blood will be partially deoxygenated. And then after birth, it's going to be completely oxygenated. So this would be significantly more oxygenated after birth than before it. So it's not going to be A. If we look at B, this is going to be point L. And again, this is going to be the vena cava before the introduction of blood through the fetal vein. Before birth, this is going to be deoxygenated because it's returning blood from the systemic circulation where oxygen has been removed from the blood, so it'll be deoxygenated at this point before birth. And after birth, it'll be the same as well. So it'll be deoxygenated before and after birth, meaning the answer in this case isn't going to be B either. Looking at C then, this is going to be point P, which is in the pulmonary vein. Now this is going to be returning partially deoxygenated blood before birth and completely oxygenated blood after birth, meaning that it's not going to be significantly less oxygenated after birth. So it means the answer isn't going to be A, B, or C, leaving D as our answer in this case. Now number 3 talks about figure 2, which I've copied out here. So we've got 2 points, X and Y. X is the point at which dye is being added at a constant rate, and Y is where a sample of blood is to be removed. We've been given an equation, which is equation 1, which is F equals Q over C, and I've written in what these values mean. Question 3 asks, the unit gram per litre is equivalent to what? Okay, so if we were to look at what this means, so we've got grams divided by litre. That would be the same if we multiply both on the top and the bottom by the same thing. If there's the same thing on the top and the bottom of the fraction, it means that we can cancel it out. And it's the same principle for units too. So if we look at option D in this case, we've got grams per min over litres per min. And we can cancel out both these minutes and we'll end up with grams per litre. So the answer for this one is D. Another way I like to think of it is that if we were to look at the numerator here, it's essentially saying this, 1 over minutes multiplied by grams, and this is going to be divided by 1 over minutes multiplied by litres. And so we can delete both of these and end up with our answer of units. It works just the same way with numbers as with units. So the answer for this one is going to be D. Okay, so looking at question 4 now, and we're given some more information, and there's a second equation here which I've copied out, which is a little bit different. It just talks about delta C, which is the change in concentration of the substance, which is important. So we're given figure 3, which looks at the difference in blood oxygenation in the right and the left side of the heart and how the lungs add oxygen into the left side of the heart. 4 asks for the situation depicted in figure 3. Point X in figure 2 is what? So remember, point X is where the dye is going to be added. So this is where oxygen is going to be added. Instead of a dye for equation 2, we're going to be looking at a chemical as introduced, so oxygen in this case. So where is the oxygen being introduced? Well, it's going to be in the lungs then. So that means that the answer for number 4 is going to be A. And then finally for question 5, for this situation depicted in figure 3, the cardiac output is what? So we're told that the flow rate of blood from the heart into the aorta is called the cardiac output. So we can just call the cardiac output F. And if we use our second equation here, we can have a look at the quantity of the oxygen added and divide that by the difference in the oxygen on either side of the heart. So the amount of oxygen being added, we're told, is 240 milliliters. And then we're going to divide that by the difference, this is the delta C, the difference in the concentration or the amount of oxygen on either side of the heart. So we can do 180 minus 120, and that gives us 240 over 60, which is equal to 4 litres per minute. So that gives us an answer for number 5 of C. So that was questions 1 to 5 of section 3 of the Orange booklet. I hope that helped. Thanks for watching.